Hi, so welcome to the third survey talk of this interspeech. And in our survey talk today, we're hearing from Karen Livescu from the Toyota Technical Institute in Chicago. Among many other qualifications, Karen is both an ISCA Fellow and an IEEE Distinguished Lecturer. And she will be telling us today about learning speech models from multimodal data.
Okay, hello everyone. Hi to everyone in Brno and to everybody elsewhere in the world. Thank you to the organizers for all of your hard work organizing this conference in this unusual situation. Let's get into it. So today's talk is about learning speech models for multimodal data. This is a survey talk, and this is a very large area, so the survey will necessarily be about a relatively small portion of it. And I wanted to start by talking about a little bit about human speech and what we mean when we say that human speech is multimodal. So this is something that we probably agree on, that human speech is multimodal, but I wanted to think a little bit about all of the things that we mean when we say that. So here are a few things that we know. We know that when we're listening to a speaker, being able to see that speaker's face actually improves our ability to understand them. So for example, these two speakers in a crowded gathering are probably better able to understand each other because they're able to see each other. And in a noisy setting, the visual signal of the speaker's face improves the effective signal to noise ratio by about 20 dB or even more. It also improves our ability to understand more complex speech or accented speech. We also know that listeners actually can't ignore the visual cues of the speaker's face, even if they try. So this is a well-known McGurk effect. If you haven't seen the McGurk effect in action, look it up online. It's very interesting and entertaining. It was discovered in adults by McGurk and McDonald in 1976 and studied also for infants. So if infants, even though they're not speaking yet, they're still subject to the McGurk effect. We also know that visual cues help children to learn phonetic segments. So this child, because he or she is able to see their caregiver's face, those visual cues help in learning phonetic categories. And it's not just about seeing the speaker's face. It's also about the visual scene that we're in. So for example, this speaker pointing to a scene is probably going to say something related to that scene, and the listener knows that. And so they have a prior on what the speaker is likely to talk about. Same goes for these doctors who are looking at an X-ray. And it's not just the visual modality. There are other modalities that come into play that are in our physical environment, things like touch, situational context, whether we're in a medical setting or outdoors or in an educational setting, that will affect our prior on what we're listening to, as well as our own internal state. Will also affect how we interpret what we're listening to. And so multimodal speech processing is about getting machines to be able to use these multiple modalities in all of these ways that humans are able to use them. And this is really not a new topic at all. Machines have been trying to use multiple modalities in speech processing for decades, at least dating back to about 1984. Models were being developed for audiovisual speech recognition, so using lip reading to improve automatic speech recognition. A little bit later in 1989, using neural networks to combine acoustic and visual cues to do larger scale audiovisual speech recognition. In 2000 and the early 2000s, Deb Roy and Alex Pentland developed an influential model for a computational model of human language learning in the presence of sight and sound. And so what has changed in the intervening years? So of course, the main thing that's changed is we have more data, we have more diverse types of data, we have more computational power to harness that data. We've developed improved models that can take advantage of all of that data and compute, and new learning techniques for learning those models. Okay. So for the rest of the talk, I want to spend a little bit of time just giving sort of a taxonomy, a partial taxonomy of ways in which multimodal data has been used in speech processing. And then I want to focus on specifically how multimodal data is used to learn better speech models. First, using intrinsic modalities, so signals that are produced by the speech itself, for learning better speech representations. And then we'll talk about learning higher level semantic representations and models from more contextual or situational multimodal data. And we'll get into all of that in more detail. So let's start with just a sort of brief tour through a few ways that multimodal speech processing has been used. So let's talk about some types of multimodal speech data. So the first general type is what I'm calling intrinsic multimodal modalities of speech. And these are signals that are generated by the speech itself, or that, that we can measure from the speaker. And so, of course, one modality that, that we associate with speech is the audio modalities, which we can measure from a microphone. We can also take a video of the speaker's face. That's another intrinsic modality. And then there are more sort of exotic modalities that have been collected for a variety of purposes, both scientific and technology oriented, like articulatory trajectory measurements, muscle activations, MRI, ultrasonic sensor signals of the speaker's facial motions. And typically, when we think about using these kinds of intrinsic modalities, we typically think about using them to improve robustness to noise, where we can assume that the sources of noise are different in the different modalities, and the two should be able to help each other denoise or remove nuisance parameters. And the second major type of multimodal data is contextual. So these are additional modalities that are not actually produced by the speech signal, but that provide additional context beyond that signal. So this might be an image that the speech is describing, as in this spoken captions data set. It might be a video that either the speaker is describing, or that is just the scene that the speaker is in, that provides some context. It might be sensor measurements from a robot, or recordings of the robot's state, that provide additional context for a robot's learning of a speech model. And typically we think of these contextual modalities as being useful for learning a more meaningful, more semantic model, or as a complementary input that gives additional information to a speech system. Okay, so what can all of these modalities do for us? So one of the most popular and active research areas involving multiple speech modalities is, of course, audiovisual speech recognition. And so this dates back to the work that I mentioned before from the 80s. And there was also a flurry of work around 2000, the early 2000s. And then there was maybe a little bit of a lull, and there's been a little bit of a resurgence recently of audiovisual speech recognition with of course, deeper and larger models and data. And usually we think about audiovisual speech recognition as a way of improving noise robustness. In the same way that humans benefit from seeing a speaker's face, we can take advantage of the video signal to improve the ability of a machine to understand the speech sounds that are being spoken, especially in the presence of background noise. Okay. And a completely different sort of way of using multiple modalities is to use contextual modalities for either error correction or contextualization. So these are complementary sorts of multimodal data. For example, in this multimodal dictation system, where the user can correct errors of the speech recognizer using different types of input modalities. Another example is the Put That There system from MIT from around 1980, which was a combined voice and gesture system that controlled a graphical interface. So this was explicitly combining information from multiple modalities to complete some task, to move something in this graphical interface. More recently, these contextual modalities have been used for improving, for example, speech recognition or speech translation in the presence of a visual context. So if we know that the speech is describing a scene, as in this example on the left, then that can bias the language model or even the acoustic model to better recognize that speech. Same goes for machine translation, as in this example on the right. Finally, we can use multiple modalities, not at test time as additional inputs, but just at training time to learn better speech models. And this is most of what I want to focus on for the rest of the survey. So we can either learn better speech representations by learning on by training on multiple intrinsic modalities, or we can learn speech models that encode deeper semantic knowledge by training on contextual modalities. A couple years back, Florian Metza gave an inner speech survey talk on the other kinds of, other uses of multimodal data, specifically using them as complementary signals, complementary inputs in systems. So that's a good talk to go back to for more on those other kinds of uses for multimodal data. And of course, there are lots of other things that I have not mentioned at all that are also important topics in multimodal speech processing, like multimodal source separation, multimodal enhancement, synchronization of multiple modality, and synthesis of multimodal data. So all of that we won't be covering, but some of what we're talking about is sort of more general to a variety of different applications. Okay, so let's get into it. Okay, so the first kind of major topic that I want to talk about is to use multiple intrinsic measurement modalities to learn better speech representations. And so to make it just a little bit more formal, this is what's sometimes referred to as multimodal representation learning or multiview representation learning. And the setting here is that our training data consists of samples of these two vectors, x and y, of dimensionalities dx and dy, or we can think of it as just a d-dimensional random vector that is naturally split into these two subvectors. So x might be a speech signal, y might be a corresponding image or any other kind of accompanying modality. And the goal is to find, to learn a representation of each of these two views that is either predictive of the other or to find a joint representation of both. And the intuition for why this is a good idea is that if we can assume that the noise in the two views is independent, then any information that's shared between views must be signal and not noise. And then at test time, we might have each view either available alone, we might only have one view, or we might have both of them. But in any case, we've learned a representation for both views. And so the picture to sort of have in mind is that these two views come from these manifolds of whatever shape, whatever intrinsic dimensionality. And if we know that they both exist and we have access to both of them, then if we add noise to one of these manifolds, but we know where the corresponding point on the other manifold is, then that helps us to reduce the noise and get back the original signal. So that's sort of the picture to have in mind here. And so I want to talk about kind of a range of techniques that have been developed over the years. And the first one is multiview autoencoders, or sometimes referred to as multimodal autoencoders. And these are neural networks that look kind of like autoencoders. So they take in some input and they try to reconstruct some input. But they have access to two kinds of input. So they either take in one input modality, as in figure A here, and their task is to reconstruct both of the training modalities, in this case, audio and video. Or they can be bimodal, so they take in both of the views as input, learn some shared representation, and then reconstruct both of them. And of course, in the case of the model on the left, that only learns a model for a representation for one modality, whereas the model on the right learns representations for both modalities. So it depends on what the downstream use is intended to be. And this comes from a 2011 ICML paper called Multimodal Deep Learning. A sort of related technique is the multimodal deep Boltzmann machine. So this is a graphical, an undirected graphical model where the collection of nodes shown here at the top form the joint representation of the two views, which are the nodes at the bottom here. They're drawn as being at the bottom and at the top just for sort of visual clarity, but this is an undirected model. And so deep Boltzmann machines have been used for unsupervised representation learning of single modalities, and this is sort of the multimodal extension of the deep Boltzmann machine. And it was introduced by Srivastava and Salahuddinov in a JMLR 2014 paper. Okay. And another technique, which is really a classic technique, much simpler than either of the two we've talked about so far, is canonical correlation analysis. This is a basic statistical technique dating back to the 1930s, but it's despite being very simple, it's quite popular and effective. So the idea in CCA, this is a linear technique. It finds linear projections of each of the two views that maximize the correlation between those projections. So that's what's shown here in this objective. It's a constrained objective. So we try to constrain the learned projections to be uncorrelated within each view so that each new dimension that we learn provides new information. And like principal components analysis, it can be solved by solving an eigenproblem. And like PCA, it has an interpretation as a constrained reconstruction objective. So we can think of it as each modality trying to predict the other with this linear model. And CCA has some well understood, nice theoretical properties where if the noise is uncorrelated across the views, then it learns sort of the right underlying linear subspace. Okay, so at this point, I want to look at a few results from those papers that I mentioned before on multimodal autoencoders and deep Boltzmann machines, comparing them to each other and to single modality representation learning when applied to audiovisual speech. So the task here is isolated word recognition on 2 data sets. Sorry, I forgot to write them here. The data sets are the Quave data set and the AV letters data set. So these are simple isolated word classification tasks. And the representations are learned either using multimodal autoencoders or deep Boltzmann machines. And either of those, so those are the bottom 2 rows in the 2 tables, either of those 2 outperform either single modality features or just a simple concatenation of video and audio features. And among the various flavors of multimodal autoencoders, it turns out to be best to train the model, train the representation so as to reconstruct audio and video when given only video input, which is perhaps a surprising finding. Some more results comparing the techniques we just talked about. This is, whoops, sorry about that. This is a cross-modal isolated word recognition task. So the task here is, now that we've learned a shared representation of the audio and the video, to learn a supervised classifier on either the audio representation and test it on video input or vice versa. So the idea is the classifier has only ever seen one modality, but because we've learned this shared modality, we should be able to switch out a different modality and still do reasonably well. And so the first set of results in the table are for training an audio classifier on the pre-trained audio representations and then testing it on video. And then below that, we have a classifier trained on video and tested on audio. And the comparison here is between the multimodal deep autoencoders versus CCA-based features. And the goal here is just to test how well these learned representations are truly shared across modalities. And one of the surprising findings here is that vanilla CCA, so this basic linear method, outperforms the multimodal autoencoders at this task of learning a shared representation. And if we add some nonlinearity, so if we learn CCA on top of restricted Boltzmann machine-based features, then it's even better. And interestingly here, training on video and testing on audio, which gets almost 92% accuracy, is even better than all of the results from the previous slide where we're training and testing both on video. So having access to the audio is certainly very helpful to the video modality here. Okay. So one of the findings here is that CCA can be improved a lot by making it a little bit nonlinear. And the next set of techniques I want to talk about are making CCA really nonlinear. So in 2013, a deep extension of CCA was introduced. And this is basically exactly what it sounds like. It is a pair of representations, each of which is modeled by a deep neural network, one for each of the views. And the 2 representations are learned so as to optimize the same constrained CCA objective as for linear CCA. And that loss is just back propagated through the neural networks. A little bit later, the idea was generalized not really generalized, but extended to a generative model called deep variational canonical correlation analysis, shown here on the right. And this looks a lot like the multimodal autoencoders, except it's a generative model. And so it's a little bit more robust, as we'll see later. Okay. And then finally, I want to talk about the multiview contrastive loss, which is very popular these days. And I call it the multiview contrastive loss, but actually it's a collection of losses, sort of different variants on this same idea. The idea is that we're learning two representations, two models, f of x and g of y, and they're arbitrary but typically deep neural network functions of inputs in the two modalities. And the goal of the learning is to bring paired examples, so examples of x's and y's that are paired, that are multimodal examples of the same thing, bring those closer together according to some distance function dist, while keeping unpaired negative examples, x plus and y minus, farther apart by some margin m. So this is a margin-based loss. And this tends to work well when it's fairly easy to find negative examples, when it's fairly easy to just sample random examples and be fairly sure that they're negative. This was used in 2014 by Herman and Blunsom to learn representations from multilingual data, to learn text representations, and it has since been applied to multimodal speech and a variety of other multimodal settings. But that was the earliest mention I found of it in a multimodal setting. Okay. Okay, so let's look at some more results applying these techniques in to a variety of different kinds of data. So what we're looking at here is learning speech representations for phonetic recognition using paired audio and articulatory measurements. So the image on the left shows the articulatory measurements. These green dots show the locations on the speaker's articulators that are being measured. This is the University of Wisconsin X-ray microbeam data set. And of course, articulatory measurements are not a modality that we expect to have at test time. So it's a good candidate for being used at training time, just to improve the speech representation. Okay, so what we're looking at here is the phonetic error rate using a variety of different representations. The baseline uses basic acoustic features, and then the remaining are all of the methods that we've just looked at: CCA, multiview autoencoders, contrastive losses, deep CCA, and variational CCA. So for this particular setting, these last three losses tend to do best: contrastive, deep CCA, and variational CCA. And that tends to hold across different settings. So just for completeness, I wanted to show a few different tasks, even though these are not speech tasks. But these are just comparisons of these basic learning techniques. The task on the left is an image tagging task measured by mean average precision, so higher is better. And on the right, we have a visual digit classification. The views here in the image tagging case are text derived from the captions and the image itself. And for the digit classification task, these are digits with two different kinds of noise added to them. So this is a synthetic two-view data set. And we can see that in general, those three models, contrastive, deep CCA, and variational CCA, tend to do best. The contrastive representation learning tends to, its quality tends to depend, like I was saying earlier, on how easy it is to get negative examples by just randomly drawing from the training set. Okay. Okay, so I want to move on to a different use of multimodal training data, and this is learning from contextual modalities, as opposed to the intrinsic modalities that we were looking at until now. So the goal here is to learn higher level speech models that encode some kind of semantic content. And the idea is that we're going to have this additional contextual modality. It might be a visual modality or it might be something else. And it informs the model about what the speech is about. Learning a model using these kinds of contextual modalities often involves learning to predict correctly matched versus mismatched multimodal pairs. So contrastive losses are very popular when using these kinds of contextual modalities. And there's been a big push to collect data sets with this kind of contextual information, typically visually grounded data sets. So for example, this is a list of data sets from a survey paper by Trupula, which contains a lot of other useful information, by the way. But this is a list of spoken caption, images with spoken caption data sets. And as you can see, they vary along a variety of dimensions, whether they're read speech or synthetic speech or spontaneous speech, and what size they are and what language they are. Most of them are English, but some of them contain Hindi or Japanese, and the number of speakers varies a lot. So they vary a lot in terms of how challenging they are to learn from. Okay. And then a related type of data is video description or video instruction data sets. So these are like spoken captions in the sense that the speech in these data sets is assumed to be about the video. But here the modalities are much less aligned than in the case of spoken captions. In a spoken caption, we know that we have an image and an utterance that's describing that image, whereas in a video description or a video instruction data set, we just have videos that are accompanying instructions, like cooking videos or car or bike care instruction videos. And so there's a lot looser connection between any given speech utterance and what it's describing in the video. But again, there have been quite a few of these data sets collected over the last few years. This is really a gold mine of data for multimodal speech models, all the way up to the most recent, I believe the most recent, the how-to 100 million data set, which includes over 100,000 hours of data from YouTube. Okay, so that's about data sets. So that's been a very active activity in recent years, is just kind of collecting these huge data sets so that we can learn models from large amounts of unlabeled data. So how do we use these kinds of contextual modalities? So one kind of large research effort has been on learning to relate images to their spoken captions. And the idea here, and I'm showing an image from this paper by Harwath et al., but many of the papers listed here are using sort of similar styles of models and objectives. The idea here is that given the images and their corresponding spoken captions, we're going to learn an image model and a speech model. And the goal is to have them produce similar representations for matched image caption pairs and dissimilar representations for mismatched pairs. And so the loss that was used in this paper looks very much like the contrastive loss that I showed before, except that it has two terms for distractors from both modalities. Most of the papers in this area use variations on this kind of contrastive loss. And the evaluation of these models is often retrieval-based, either given an audio signal, retrieve an image, or vice versa, or find nearest neighbors and evaluate the quality of those nearest neighbors, or evaluate the quality of the similarity between the model's hypotheses of matched pairs versus human judgments of similarity. So that's what I refer to as retrieval-based evaluation. Okay. So what else can we use this kind of visual grounding for besides learning retrieval models? So it turns out that they can be quite effective for learning or locating objects and words that correspond to the same category. And so this is an example from this paper by Harwath et al. On jointly discovering visual objects and spoken words from unlabeled spoken caption and image data. And what you're seeing here are regions in the image that correspond to a particular word. So for example, the word building corresponds to these regions in these three images. And you can see that at least for these examples, the regions do tend to correspond nicely to the spoken concept. And the same idea has been applied to learning matched objects and words across languages, meaning if we have spoken captions in multiple languages, we can learn this multimodal model for each of the languages and the images. And then that helps us to learn a bilingual lexicon by discovering these clusters of associated objects and words and then associating them across languages. Okay. What else can we do with visual grounding? So we can also learn to do speech-only tasks, like retrieval or query by example, or even cross-lingual keyword spotting. And there's a line of work mostly led by Herman Kamper and others that focuses on these kinds of tasks. So using the visual grounding to learn a pure speech model for speech tasks rather than a cross-modal model. And most of these papers are based on the idea of taking these spoken caption data sets and then taking a more or less off-the-shelf image tagger, which provides noisy or weak text labels. So we take an image, tag it with the image tagger, which produces posterior probabilities of these semantic text labels. And then we treat those as labels for the speech model. And then we learn a speech model that learns to map from the acoustic input to this bag of semantic tags. And now we have a model that doesn't need the visual modality at all. It just goes from speech to semantic tags, and it can be used to do things like retrieval or query by example or keyword spotting. And the same thing can be done cross-lingually because we don't rely, because we can use a tagger that tags images in any language. And so we can learn to map from the speech in some language to tags in some other language. Okay, so that was sort of a brief tour of those two general approaches to learning from multimodal data. There's a number of open questions and sort of directions for future work, and I just wanted to spend a few minutes discussing those. So one question that's begun to be explored is what is the right way to combine more than two modalities? So a lot of the techniques that I've described sort of assume that we're dealing with two modalities. They can be extended to more than two modalities, but that extension isn't always obvious or computationally convenient or well understood theoretically. So for example, for CCA, there a number of many view extensions dating back to at least the 70s, and they've been used in recent work, for example, for learning from many different signals in open domain videos, including speech and the video and text. But it's not obvious what is sort of the right way to extend the idea of CCA to many views. And so this is very empirical work, just sort of trying different approaches. Same goes for contrastive losses. There are many view extensions of contrastive losses. There's a paper here at Interspeech this year by Rudachenko et al. About learning from instructional videos using a number of views. So I won't go into that. You can see the paper. But again, we don't have a great understanding of what is the right way to do that. And sometimes it's very computationally demanding to extend these objectives to a large number of modalities where, for example, we're searching for negative examples across multiple modalities. And we also don't have a very good theoretical understanding or even intuitive understanding of what they're doing. So I think that this is an interesting question for future work. Another question is that just like many other recent deep models, we'd like to have a better understanding of what's going on under the hood, especially when we're going from a very surface representation like acoustics to a very deep semantic representation. And there's been quite a bit of work actually on trying to understand what's going on in these, sorry about that, inside these models, like Trupala's work on looking at which layers in the models correspond to which types of linguistic signal, and some of the work that was done at the JSALT 2017 workshop at Johns Hopkins and on the Speaking Rosetta Stone project. There's also been work on sort of intrinsic evaluation of multimodal models. So for example, at the Zero Speech Challenge in 2021, track 2 is actually using video to learn a better language model of audio. So Zero Speech has a suite of evaluation techniques to try to assess what kind of information is encoded in these models. So I won't say too much about that. It's in progress. I guess we'll see in a few months what comes out of that. Another sort of big area is using a more diverse set of modalities. So most of the work that I've talked about here focuses on images or video as the non-speech modality. Sometimes we also have text, but we need more work to sort of understand the usefulness of other modalities. How should we be using situational context or world knowledge or other sensors that we have access to? And I guess one field that's looking into that is robotics, but there hasn't been a great sort of very active collaborations between robotics and speech. Of course, there are some, but maybe we just need more representation of robotics at speech conferences, which would allow us to consider a wider variety of sensors. And I think it might also be time to think about more diverse learning methods. So some of the older work that I described here on multimodal and multiview representation learning developed and compared a whole variety of models and losses, whereas recent work has focused, very appropriately on collecting new data, on new data settings, but has stuck mainly to a certain type of model, certain type of contrastive losses. So this might be a good time to start thinking about what other kinds of objectives and models can we be using to get to squeeze more out of these models. Finally, or almost finally, most of the work that I've surveyed here is assuming that we're in a purely unsupervised context. And that's kind of a very nice, clean setting to study. And it has a very nice scientific feel that we're learning what we can learn from purely unsupervised data. But in practice, we do often have access to at least some small amount of supervision. And so I think we need, some better understanding of how supervision interacts with multimodality. So if we have some supervision, do the additional modalities still help? What is the trade-off between collecting more supervision versus more multimodal data and all of the computational trade-offs that are involved? Again, there's been some initial work addressing these questions. So in the context of the models that I described for learning speech retrieval from visually grounded speech, we've seen that the visual modality and textual supervision, when available, can be complementary, at least in a low resource setting. Presumably when you get to a high enough resource setting, then the supervision sort of trumps everything else. There's also been some other work on looking at how to add textual supervision for better spoken language understanding. That was at EMNLP last year. But I think we need kind of a lot more structured work trying to understand this whole space of supervision versus multimodal data. And then maybe a final question that I'm going to leave with is all speech actually groundable in some other modality or modalities? The work that I described here that's been done recently on visually grounded speech tends to focus on very visually salient physical scenes that are being described. Is this all that these models can do? Are they able to also generalize to more abstract domains? If so, how? If not, how do we combine multimodal grounding with some other kind of signal to learn more general language? So that's kind of a very broad question, and I don't know of work that's actually looking at that yet. So I think that's a good place to stop. I want to thank you for your attention, and I'll be happy to take any questions.
Okay, so it looks like we have Karen connected here, so we can start by taking any questions from the room.
And I would like to also remind the remote audience that you can also ask question in the by the text in the next to the video. Okay. We have already some.
I have a question. Karen, thank you for your talk. And I have a question regarding the sampling of negative examples, because sometimes the negative examples could be classified as negative just based on some basic properties like video length, because if you compare positive and negative examples and they differ in the length, you can easily say that this is the negative example. Is there some better way, or do you have experience with better ways how to select the negative examples?
Yes, thanks for the question. Can everybody hear me okay?
Yes.
Okay, great. So there's been a bit of work on sort of different varieties of contrastive losses and different uses of negative examples. I think, so of course, it's the problem that you bring up is that it's important to make the task of distinguishing between the negative and the positive examples sufficiently difficult to learn something. I think people tend to focus on the other problem of not picking up on negative examples that are actually positive examples, because we're usually just drawing random examples from the data. And so I think for the question of making it hard enough, we tend to just sort of rely on intuition, like drawing data from a sufficiently large mini batch that if we draw a few negative examples, then there'll be some in there that are difficult to distinguish. And a lot of work on contrastive losses also looks at how to combine different negative examples so that if you end up with one being too easy or too difficult or a false negative, then some of the others make up for it. But I don't know that this is necessarily very well understood. I think that's still an active area.
We'll take the next question from online.
So we have here a question from Ephraim Loimi. I hope that I didn't screw up the name too much. So it's from University of Edinburgh. Thanks for great talk. Do you think that an effective multimodal learning, the training/learning dynamics for different modalities should be similar? For example, in pairing the audio with video, if learning from audio converges faster than learning from video or context, the learning will be dominated by one modality, and this possibly limits the advantages of multimodal learning.
Okay, so I think the issue that you're bringing up is that you're often learning multiple representations for different modalities, and some of them might sort of converge faster than others. And I think that's true, and I think that's also a little bit of an understudied issue. I mean, I think that we all have kind of our favorite optimization tricks and hacks, but I don't think that they're very often reported on, and so that's not a problem that that I think has a general solution yet. In a lot of these sort of settings, we have a fairly limited amount of multimodal data, and so we rely on actually a pre-trained model for each of the modalities from some other domain. Like, for example, an ImageNet model for the visual data. And so very often what we end up doing is not actually updating, say, the initial several layers of the model from one modality that we have a good pre-trained model for. And focusing only on the multimodal part. And so I think at the moment it's a fairly kind of empirical process to decide on how best to trade off between what we're optimizing in the two modalities.
We have another question here in the hall.
Yes, so I will certainly agree to bring back robotics in the field, but I think for multimodal integration, I think neuroscience will be perhaps more interesting. You didn't mention this. Why?
Okay, that's a very good question, and I probably should have. Let's see. How do I make up for that? So, so there has been some work on sort of multimodal. Learning from multimodal speech data paired with neural signals. And I think maybe I didn't mention it only because there hasn't been kind of as unified a body of work, but it's, I agree that it's very interesting and falls under a similar category of learning from signals that we can't really hope to have a test time, but that we can learn useful information from at training time. So there's been, for example, very interesting work at Google by Malcolm Slaney and others on using neural signals paired with speech to learn what sort of a listener is attending to. And yeah, I guess next time I give a talk like this, I'll have to include more neural signals.
We have more questions from the audience here.
Yeah, thanks for this very nice talk. So what I was going to ask is a bit related to the first online question we had. So we've got several modalities, for instance, in speech recognition. Yeah, and these modalities may have got very different performance characteristics. For instance, we might have got sounds which are easily distinguishable from audio. We might have got sounds which are better distinguishable from some articulatory data, and then we get some noisy audio, and then the situation changes again. And I was wondering what you can say about merging the situation that you've got data sources with very different properties, with changing properties, and with properties which might not appear in the training data.
Mm-hmm. So I think that this is actually a problem that used to be addressed a lot more in sort of the early days of audiovisual speech recognition. These days, I think we're still at the stage where we're just building huge models from huge data, and we don't have a great understanding of them, though hopefully that's changing. But in the older work on audiovisual speech recognition, at least, there was a lot of attention paid to the fact that you know, some phonemes are more distinguishable from the acoustics and collapse into the same visual category, which is referred to as a viseme. But then some kinds of acoustically challenging distinctions, like among nasals, might be easier to distinguish from the visual modality. And so there was quite a bit of work on learning how to weight different modalities to account for dynamic changes in what's most salient in different modalities. So there's a lot of work on optimally reweighting or dynamically reweighting. And I think these days that hasn't quite happened yet with these newer models. But there's probably a lot of room for that as we kind of settle down and move away from just building larger and larger models to kind of understanding better what's inside them.
We have another question from online.
So Mikko Kurimo from Aalto University is saying, thanks for the great talk. Any ideas of architectures to solve the temporal alignment? For example, speech on video may describe things that happen in past, not at the same frame as the words are uttered.
Yeah, that's a great topic. And I myself have not worked on those spoken description data sets, so I can only sort of relay what I've gathered from the literature. I think that a lot of the work on video description relies on the fact that there's kind of an approximate alignment, and so we assume that if we have a clip of a certain size, that it will include some speech that's about the video going on in that clip. And the trick is to kind of, for any particular data set or any particular domain, to have the right size of clip. But I think longer term, as we move to more and more naturalistic settings, more just dealing with found video from the internet, it will be interesting to think about more carefully modeling the alignment between the modalities. So for example, I imagine that cross-modal attention models will have a much bigger role as we start to look at things that are less well aligned. So I do think that that's an interesting question to address with some of these newer and noisier and more diverse data sets.
I think we have time for one more question. Okay, I'm not seeing anything in the hall or online.
Well, maybe I wanted to ask one thing. So if I understood well in the first part of the talk, you are actually trying to come with the representation from audio and video, but those were on the frame level, right? If I understood it well, so it would be on the feature level. Maybe can you say so? And then in the second part, there was basically some global embeddings, which were embeddings of the whole audio or whole picture. So can you tell us a little bit about what were actually the inputs on the from the audio and from the video, just to get the idea? Was it MFCC frames and the images themselves, or was it some specific representation of it?
Are you asking in that first part?
Yes.
Okay, yeah. So there were a few different data sets there, and you're right in that sort of setting where we're measuring sort of multiple modalities that are produced by the speech itself. We assume that there's more or less very, very good alignment between the different modalities, and that each frame or small clip of signal is referring to really exactly the same thing. And so let's see, there were several data sets that were used there, but typically it's you know, a typical speech frame versus whatever is happening in the other modality during that span of time. And so if it's the articulatory data set, then there would be typically a different sampling rate for the articulatory data, and then you would end up kind of averaging one of the modalities to match the frame rate of the other one. For things like the Quave and the AV letters audiovisual data sets, yeah, it would be on the frame level. There, the video frame is typically at a slower rate than the audio frame, so there's some pooling going on before matching them up. I don't know if that's addressing your question.
Yeah, I think so, yes.
Okay, thanks.
So I think we need to bring the session to the end, but let's thank Karen again for a great survey talk.
Thank you, everyone. Have fun.